Okay, so week 13, Thursday. This is the second last lecture. Our agenda will be on maximum distortion energy theory. Okay, so let me describe what is the maximum distortion energy theory first. So the distortion energy in this stage is measured in per unit volume. Okay, and is under plane stress condition. So when the term plane stress comes, okay, it means that, okay, what is plane stress? Just to quickly recap, plane stress condition is where at least one of the stress vector, okay, sorry, not any stress, normal stress vector is equal to 0. Okay, so that's what we mean by plane stress. So we are just going to apply the energy equation. Okay, I'm not going to describe how it's derived. Okay, so the energy, so UD, capital UD, is equal to 1 over 6G, right? Normal stress squared, okay, minus by stress A, stress B. I will describe what is stress A and stress B later on, plus by stress B squared. Okay, I'm not going to derive this equation. We are just going to apply this equation. Okay, so this is our equation number 1, where UD is our distortion energy. Okay, and stress A and B are the principal stresses, and then G, that is C over there, is the modulus of rigidity. Okay, and I think all of us have seen an equation that's related to modulus of rigidity, is where we have this expression, okay, sigma tau is equal to G multiplied by gamma, where this is known as our shear stress, gamma is our shear strain, and G is our modulus of rigidity. So this formula looks very familiar because we have something for normal stress, right? right? If I write this expression, you go, oh, I've seen this before, right? Where this is known as normal stress. Sigma is our normal stress. E or epsilon is our shear strain. And capital E, our Young's modulus. So G is to use in shear. Young's modulus E is for normal stress. Okay. So let's look at an experimental setup under uni-axial test. Okay, so uni-axial. Let's look at uni-axial or unidirectional. Experimental setup. Okay. So if we have a rod, okay, let's assume that it's going through tensile. Okay, that's our centroid, and then we have opposing forces in the x direction. So if I would draw our transformation, this is x, this is y, and that is our z. So if we view this, right, in the y and z configuration, sorry, y and x, and we put an element over here. Okay, so when we draw it out, right, if we look at the front view, we only have one stress state, and that stress state is sigma x. Okay, so if we were to call this x and y, right, and we know stress z is equal to 0, right? So if we were to do this based on experimental loading condition, okay, and when we construct mole circle, okay, so I'm going to draw mole circle based on the stress state of our uni-axial test, okay, based on our uni-axial test. So if we were to construct mole circle, this is our normal stress, and then we have our shearing stress, right? So we have our normal stress, shearing stress, element rotate clockwise, element rotate anti-clockwise. Because there's no shearing in our uni-axial test, over here, this is our stress X, this is our stress Y, and this is 0. And when we construct our mole circle, we know over here is our point X, over here is our point Y, and it's also equal to our point Z because our Z stress state is equal to 0. So this is our mole circle now. Okay. And that's our mole circle. So we know from here, right, our principal stresses, right, we can also call this point, okay, our stress A, right? Over here, this point is our stress B, right? So when stress A is equal to stress capital Y, okay, and stress B is equal to 0, we're going to substitute the entire equation into equation number 1, okay, and I'm going to declare stress capital Y is our U strength. So from here, okay, I'm going to write out a term as we will have U D, and this is Y, okay, and this will be equal to 1 over 6G, right? So we're going to substitute into equation number 1 that look like this, right? It's stress A squared minus stress A multiplied stress B plus Y stress B squared. And we know that stress B equal to 0. So when that's the case, we substitute in here, get sigma Y squared minus by sigma Y multiplied by 0 plus by 0 squared. Okay. In the end, we will get sigma Y squared divided by 6G. Okay. So this is von Mises criteria. Okay, and sigma Y, right? You know that over here, this is a material mechanical property. Okay. That is our material mechanical property. So that is the criteria, right? So we will grade the structure as safe. Okay, so the structure is safe, right? When UD, right, is less than UD U. Oh, I'm going to put Y down here, right? So UD that you see over here, this is based on structure analysis. Okay. UD with a Y, capital Y at the end, is the material mechanical property. Okay. There's a material mechanical property. And this equation, I'm going to call this equation number 2, right? We derive this equation number 2 over here, based on a unidirectional experimental setup. Okay. Whereas over here, we just apply a energy distortion equation. Okay. So now, if we were to relate equation 1 and equation 2, okay, we're going to put both of them together, right, to satisfy this condition over here, right? So our UD is equal to 1 over 6G sigma A squared minus sigma A sigma B plus by sigma B squared. And this has to be less than 1 over 6G sigma U squared, right? So we can get rid of these two terms over here. And then we have a relationship where we have sigma A squared minus sigma A sigma B plus by sigma B squared must